So we had a discussion on the KL transformations in the last class, and today we are going to compare all the different transforms which we have discussed so far, naming the discrete Fourier transform, the discrete cosine transform, the Hadamard transform, and the KL transformation. I mean, of course, the results will also be compared with the Haar transforms and the slant transforms, which we did not discuss actually. So all these comparisons will be shown in today's class, and thereafter we will go over to yet another transformation which is based on the singular value decomposition. So first let us have a comparison between the several transformation techniques which we have discussed. Now in the transformation techniques comparison, what we are going to do is something like this. There should be certain basis on which we are going to make our comparison. Now for this matter, what we are doing, we are taking 4x4, I mean a typical 4x4 element, okay, 4x4 image, okay, as a basis, okay, and then we are going to study all the different transformations, okay, and see that what is the percentage of error that it leads to. All right. So at first what we will have is a comparison of the variances, meaning that we will be comparing the various frequency components, rather the energies of various frequency components in the transform domain. So what we are going to do, this is a typical curve which is there, okay, for comparing the image transformations. On the y-axis we have the variances, okay, and on the on the x-axis we have the various indices of k. Now what we have done is that we have taken the index, okay, in the x direction, and then we are going to have a comparison of various image transformations. All right. Now as you see over here that this is the lowest index, meaning that this corresponds to the lowest frequency, okay, or the DC component, and on this axis, this way we are going over to more and more higher frequency components. All right. Now you see over here that at the lower frequency component, okay, this is the this is the virtual starting point for all the transformations, meaning the variance is starting from roughly a value of 10, okay. From a value of 10 the variances are starting, and just see that as the index is increasing, okay, the values are coming down. And let us see that which component, which transformation has which nature of curve. At first let us have a look at the cosine transformations and the KL transformation. You see the curve which I am tracing right now, this gives us the cosine transformation, and the curve is absolutely merging or almost very closely merging with the KL transformation. Now what is the characteristic of this curve? You just see over here that as the index is increased, okay, we are finding that the variances are decreasing steadily, okay. That means to say that for these two transforms, KL transforms and cosine transforms, okay, maximum amount of energy is packed in the lower frequency components, okay, and the higher frequency components are having much lesser energy as compared to this. So that means to say that the energy compaction characteristics for the cosine transforms and the KL transformations are better as compared to the other transforms. Now you just see, I will show you the nature of the discrete Fourier transformation, okay, unitary DFT. I am tracing the curve for this, okay. The DFT curve is going like this. All right. Now you clearly see that for the DFT, okay, although the variance is decreasing steadily, okay, with k, but still we find that the curve is generally located much above the cosine and the KL transformation. So that means to say its energy compaction is not as good as the cosine and the KL transformation. The curve for the sine transformation is as follows. For the sine transformation, the curve is traced like this. All right. For the Haar transforms, okay, the curve is going like this. Haar, or rather, let's have the Hadamard transformations. For the Hadamard transformation, the curve is following a nature like this. Okay. Haar is slightly above Hadamard, so that means to say that Haar's energy compaction is worse as compared to Hadamard, which we had discussed. Okay. And you see that Hadamard transform, the sine transform and the discrete Fourier transform, the curves are much above the discrete cosine transform and the KL transformation. Okay. So which means to say that obviously in terms of the energy compaction, the discrete cosine and the KL transformations are much better as compared to others. Okay. Now we are going to see yet another interesting result, that is that out of the 16 frequency samples, okay, we are going to see that if we retain only a part of the frequency domain samples. You remember that last time we did like that, we were retaining, I mean out of the capital N number of frequency samples, we were retaining only small m out of them, okay, and rejecting the rest of them, I mean rejecting the remaining. So we are going to retain only a small fraction, okay, of the total number of samples. Now totally in the frequency domain we have got 16 samples, as I already said. So this axis is showing the number of samples retained. It begins with 0 over here, 1, 2, 3, 4, 5, 6, etc., etc., and this is 16 samples retained. 16 samples retained means what? That we are retaining all the samples in the frequency domain. So obviously what should be the error for that? The mean square error? Mean square error is going to be 0 because we are retaining everything. Alright. Now again the curve which has been shown, okay, gives you a nice comparison between the various transformation. On this axis we are having, if you remember in our last time's discussion we had defined a factor called, a parameter called j suffix m. So on this axis we are having that j suffix m, which is the nothing but the mean square error when we are retaining only m out of the total n number of samples. Alright. So Jm is the mean square error, and what we have just done is we have represented the mean square error, okay, in terms of percentage, okay, and on the y-axis we have plotted this. This is the mark for 5%, this is for 10%, this is for 15, this is for 20, this is for 25, and this is for 30%. Alright. This is the mean square error, and this curve, should it start with 0? Well, 0 samples retained means we are not retaining anything. So that is of course a meaningless entity. So in the worst case we should start with just 1. Just 1 means we are retaining only the I mean the first sample only we are retaining. We are retaining only one sample and rejecting the, I mean all the remaining 15. Okay. Apparently the performance should be extremely bad, isn't it? Because only 1 out of the 16 samples are being retained. Okay. Let us see that how that performance is. So I will follow this curve and see that what is there when I am retaining only one sample out of 16. Okay. Now I find here that roughly around 23% of mean square error I am incurring in the process. If I retain only one sample, there is about 23% of mean square error. High, no doubt, but not something which is absolutely bad. Okay, 23% of mean square error is there when I retain just one sample, and that figure is there for the cosine, KL transform, Hadamard transform, slant transform, Hart transform, DFT. All of them are giving this figure of roughly 23% when only one sample is retained. For the sine transform, the amount of error which we are incurring in the process is around 30%, which is fairly high. Okay. Of course, retaining only 1 out of the 16 is obviously too poor, but let us see that what results when I retain, instead of 1, I retain only 2 samples. So what I have, if I retain 2 samples, I reach approximately this area of the curve. Okay. Now this area of the curve is of course what I get for the cosine and the KL transform. For the cosine and the KL transform, I am getting a figure of roughly 10% of the mean square error. The mean square error is already coming down to only 10% when I am retaining 2 samples out of 16. Alright. And for the other transforms, that is to say for the Hart transform and the DFT, the figures are a little bit on the higher side. Roughly you can say that for 2 sample retention, Hart is giving us a mean square error of roughly 12%, okay, whereas the discrete Fourier transform is giving us a mean square error of around 17 to 18%, and the sine transform is giving us a mean square error of the order of 20% or so. Sine transform is obviously on the higher side as we see out of all the transforms. When I retain only 3 samples out of 16, okay, you see that for the cosine and the KL transform, the curve has drooped further and I am getting a mean square error of the order of only 5%. Okay. Just I have retained 3, rejected 13, and I am getting a mean square error of only 5%. Alright. Of course, the same figure for the Hart transform is on the higher side, maybe around 8% or so. For the DFT also a similar figure of 8% or so is there, and for the sine transform it is little above 10%. When I take 4 samples or 5 samples, okay, obviously the curves are falling down further and further. Let me try to trace the curve for the cosine and the KL transform, which is giving us the best performance in terms of the mean square error. The cosine and the KL transforms curve can be traced like this. The one which is at the bottom is the, which I have just now redrawn over here. This is the cosine and the KL transforms percentage. Just see how good it is. If you were retaining only 8 samples out of 16, that means to say, if you retain only 50% of the samples, the mean square error comes down for these 2 transforms, cosine and the KL. The mean square error comes down to roughly 2%. And believe me, if you are seeing the reconstructed image, okay, you will not find, I mean virtually you will not find any difference, okay, when you are reconstructing the image after retaining 50% of the frequency samples. Even if you retain 25%, that means to say 4 samples out of 16, the error which you are going to make is 3 or 4%, okay, and even there also you will not find any objectionable result when you are reconstructing the image. So that means to say that you can clearly pack, okay, information, you can clearly make a comparison ratio of 4:1, okay, just by going over to the transform domain. Instead of representing the image in the spatial domain, if you are representing in the transform domain by applying the KL transform and the cosine transform, roughly 25% of the frequency samples are sufficient to make a reasonably good effect of the picture when you are reconstructing it by applying the inverse transformation. Okay. The sine transformation result is of course on the higher side. This is the sine transform. Okay. The curve goes like this. Okay. And roughly somewhere around this point, the sine transform curve is almost merging with the cosine and the KL transformation curve. And Hadamard is falling somewhere in between, but the only characteristic is that in the case of Hadamard and the Hart transforms, basically the Hadamard and the Hart transforms are the, basically they take the digital values, okay, in their transform coefficients, and there we are finding that the curve is on the higher side whenever we are retaining relatively larger number of samples. So that means to say when the number of samples retained is greater than 8, say 10, 11 and or so, okay, we are finding that Hadamard transform is not giving us a very good performance, okay, mean square error wise, okay, but for smaller percentage, okay, it is somewhere in between the sine transform and the cosine and KL transform. So again, this comparative figure indicates to us that the discrete cosine and the discrete KL transforms are quite good in performance. Alright. Now, I am going to show yet another result in which what I have done is that that we have reduced the samples. That means to say instead of instead of taking all the samples, we have reduced the samples by first we are taking the sample reduction as 2:1. That means to say 50% of the frequency samples are retained, rest 50% rejected. This is 4:1, that means to say 25% retained. This is 8:1, that means to say 12% retained. And this is 16:1, that means to say only 6% of the total number of samples are retained. Okay, and we are finding the normalized mean square error, okay, for all the different transformations. Now in this axis it is the sample reduction ratio. On the x axis we are drawing the sample reduction ratio on this axis, and on the other axis, on the y axis, this is the normalized mean square error. Okay, and just see, if you are retaining only one sample out of 16, okay, in the final reconstructed image, this normalized mean square error which we are indicating here is the mean square error in the final reconstructed image. That means to say the mean square error between the original image and the reconstructed image. Okay, when the sample reduction ratio is 16:1, okay, that means to say only 1 out of 16 samples are retained. Okay, it is giving us a normalized, the DFT and the cosine transform is giving us, the discrete cosine transform and the KL transform is giving us a mean square error of 4.5% roughly. 4.5%, okay, in the reconstructed image, okay, as compared to the original. Mean square error with respect to the original image is only 4.5%, whereas in the case of the Hart transformation we find that it is highest, of the order of 8.5% or so. When the sample reduction ratio is 8:1, already for the cosine and the KL transform, the normalized mean square error has come down to 2%, okay, whereas the other transformations, the slant transforms, the Hadamard transforms and the Hart transforms are on the higher side. All right. When sample reduction ratio is as high as 2:1, that means to say we are retaining as high as 50% of the total number of samples, then the normalized mean square error comes down to roughly 0.5% for the case of the cosine and the KL transform. Okay. For Hadamard transform it is roughly 1%, for Hart transform it is nearly 2% or so. Okay. So that means to say that in these transformation techniques, all the time we find that the discrete cosine transform and the KL transforms, okay, they are giving us much better performance as compared to the normalized mean square error. Okay, means with taking the normalized mean square error as a basis of comparison, we are finding that the DCT and the KL transformations are giving us better performance as compared to the other transformation techniques. Okay. Now, again out of the discrete cosine transform and KL transform, if we try to make a comparison, okay, which one should we prefer out of the two? Okay, there is a question. Which one should we prefer? Whether we should prefer DCT or whether we should prefer KL transformation, okay, if we find that the normalized mean square error is almost the same. Of course, theoretically the normalized mean square error is going to be least for the KL transformation, but we are finding that for all practical results the curves for the DCT and the KL transformations are almost merging. So if the mean square error is same, almost the same for the DCT and the KL transformation, which one should we prefer? What do you think? DCT. Okay, what is the reason that you feel that DCT should be preferred as compared to the KL transformation?
It is independent.
Yes. What the correct answer which has been proposed over here is that the DCT is very much independent of the image. Okay, so you can compute all the basis functions as well as the basis images, okay, beforehand. Okay, and then what you need to do, you just have to apply that transformation on your image, and you can do it using a very fast algorithm, a fast computational algorithm. Whereas for the KL transformation, we have seen that KL transformation is heavily image dependent, alright, and no simple technique exists for finding a fast KL transformation, okay, because the transformation matrix is not known beforehand, okay, whereby we can try to decimate the transformation into smaller and smaller sequence lengths. Alright. So that is the reason why the discrete cosine transforms are finding a very wide applications, okay, in the field of image data compression and coding, okay, because our performance chart as we presented over here clearly shows that even by retaining 50%, I mean 50% retention gives an excellent performance. Even if you retain 25% of the samples, it is still giving a reasonably good results, okay, for the DCT. Now, in the KL transformation, we found that theoretically KL transformation gives us the optimal result in terms of the mean square error, okay. Its energy compaction is really excellent, okay, theoretically that is the best that one can get. Now, we had also said that the KL transformation is image dependent transformation. But when I said image dependent, okay, I think I should qualify this image dependency, okay, a bit more. What do I understand simply by image dependency? Supposing I give you a single image, I give you just one image, okay, do you think you will be in a position to find out the KL transformation for that image? Do you think so? You don't think? What is the reason that you feel that just a single image will not give you a KL transformation?
Finding KL transform, we require probability distribution of each pixel.
Well, you just go back to our expression, okay? You just go back to our expression and you find that we have to determine the correlation matrix. And what is the correlation matrix? It is nothing but the expectation of U transpose, okay? And that gives rise to a n by n matrix, okay? If U is an n-dimensional vector, okay, then U of expectation of U transpose, okay, in the vector form gives us an n by n correlation matrix. Now, whenever we are saying expectations, okay, naturally that expectation is to be calculated over a sequence of images, all right. So, it is so possible that if the image, instead of being a single image, it is a sequence of images which are coming to us. Let us say TV images, okay, which are coming in sequence, all right. It is, it can be divided into a number of frames, okay. So, frame by frame, a sequence of images are coming from the TV signal, or from the video, we are getting a sequence of images. So, wherever we are getting such kind of sequence of images, then it is understandable. Then for that particular sequence of images, okay, or rather for an ensemble of images, okay, I can compute the expectations. And if I can compute the expectations, I can compute the correlation matrix. And obviously, if the correlation matrix is known, then its eigenvalues and eigenvectors are known. And once the eigenvectors are known, I can compose the transformation matrix, and then I can apply that particular transformation matrix on the next set of images which are coming to us. So, KL transformation, when I said that KL transformation is image dependent, okay, don't be under the misconception that KL transformation is dependent upon just a single image. If I get just a single image, I cannot compose the KL transformation matrix. I need a sequence of image or an ensemble of images. Now, we are going to discuss a transformation, okay, which we can derive from just a single image, okay, and that image also, I am making a generalization that that image need not be a square image, that is to say, it need not be an n by n image, it could be any general m by n image, okay. And let us consider an image U like this. We consider an image U, okay, which is a two-dimensional matrix, and this two-dimensional matrix is of size n by m, all right. So, that means to say n rows and m columns, all right. And let us assume that this image is composed of all real elements, okay. I mean, that is how a normal picture is, okay. It consists of all real elements. So, I am assuming that the image is real, and I am also assuming that capital M is less than or equal to capital N, okay. Now, I am going to consider, okay, two matrices. One matrix is the product U transpose. What is the size of U transpose? N by N, okay. U transpose is of size N by N, and I am going to consider yet another image, okay, which is U transpose U. What is the size of this image? m by n, and I am going to consider, okay, the rank of this matrix. This rank of this matrix U, okay, I am assuming that it is equal to R. So I assume that small r is the rank of the matrix U. Alright? So what I am going to do now is that since m is less than or equal to n, okay, there are at most how many number of eigenvalues? There are at most R is the rank of the matrix, okay. So I have R less than or equal to m non-zero, of course I should have said non-zero, R less than or equal to m non-zero eigenvalues are existing. Alright? So what we can, I mean eigenvalues of what? Eigenvalues of obviously eigenvalues has to be for the matrix U transpose or the matrix U transpose U. So for both U transpose and U transpose U, okay, we have R non-zero eigenvalues. I have assumed that m is less than or equal to n, okay, and R is the rank of the matrix. So we are going to have R number of non-zero eigenvalues, okay, and the eigenvalues are going to be equal for U transpose as well as for the U transpose U, okay. So there are R number of eigenvalues, and then I can write U transpose U, okay, which is of the order m by m, okay. If I multiply this by another vector phi m, okay, assume that this is being multiplied by a vector phi m, okay, this is equal to lambda m phi m, where, I mean, if it satisfies a relation like this for a vector phi m, what should you call? Phi m is the eigenvector. Phi m is the eigenvector, okay, phi m is the eigenvector. And what is lambda n? Lambda n is the corresponding eigenvalue. Is the eigenvalue. And phi m is the eigenvector of which size? It has to be an eigenvector of? Not n, because U transpose U is of size m by m. So phi m has to be an eigenvector of size m by 1, okay, and lambda m is the corresponding eigenvalue, okay. And what is the index of m? What are the limits for m? M can vary between 1 to r, yes, m can vary between 1 to r, alright, because there are R number of non-zero eigenvalues. R, again I remind you, R is the rank of the matrix U. Alright. Now, again, the same eigenvalues lambda n's are going to be there for the U transpose matrix. Alright. So this I have written for, these are the eigenvectors for U transpose U matrix, and now I am going to consider the U transpose matrix and their eigenvectors. Okay. So matrix U transpose, okay, I am going to multiply this by the eigenvector. What should be the size of the eigenvector? N by 1. So let me now write the vector as phi m. Phi m I have defined the eigenvector of size m by 1. Okay. This is the eigenvector of U transpose U, and now I am going to consider the eigenvector of U transpose, which I am considering that eigenvector to be psi suffix m, being the mth eigenvector. Okay, and that should be equal to what? Lambda m psi n. Excellent. Okay, where psi n is the eigenvector of u transpose. Okay, and what is the size of this eigenvector? It is size n by 1. Okay, and even here also the index m can vary 1, 2, 3, 4, etc. up to r. All right. Now, what we are going to do, we are composing two matrices. Okay, the first matrix I am composing with this phi m eigenvectors. With this phi m eigenvectors, I am composing an eigenmatrix, and I am calling it as the matrix phi. So matrix phi, okay, is composed with phi m as the mth column. Okay, and the matrix psi I am composing with the vector psi m as the mth column. So what is the size of the matrix phi? The matrix phi is of size m by r. So phi's size, okay, size of phi is, obviously there are r such eigenvectors are there, okay, and each eigenvector is having totally m number of we are having phi m is the mth column, so the size of phi is going to be m by r. All right.
Psi will be nth column. M is varying from 1 to r.
Well, phi m's are the columns, and there can be r number of such columns. Okay, there can be r number of such columns because there are r number of eigen vectors. Okay, and this is of dimension, as I already told, that phi m is of dimension m by 1. So there are m elements over here, okay, and there are r such columns. So it is m by r. Alright, is that understood? And the size of psi matrix is very similarly an n by r matrix. Okay. Now, if I compose two such matrices, eigenmatrices phi and psi, okay, I can represent the image matrix U as follows. Then the image matrix U, okay, can be written as the product of the psi matrix, then another matrix which I am denoting by capital lambda to the power of half. I will explain what matrix it is, and this multiplied by the phi transpose matrix. All right, and I tell you what this big lambda to the power half, this matrix stands for. This matrix basically stands for an r by r. This stands for an r by r diagonal matrix, okay, whose each element is given as follows: lambda 1, square root of lambda 1, etc. Square root of lambda 2 is the next diagonal element, and the last diagonal element is square root of lambda r. Okay, and all the rest of the elements are zeros. Okay, rest of the elements in this diagonal matrix is equal to 0. So this is an r by r diagonal matrix whose each element is the square root of the eigenvalues. All right, and this can be written in the series form as m equal to 1 to r, okay, square root of lambda m psi m phi m transpose. Okay. Now this representation, okay, this representation of an image. So basically what I have done, I have now represented the image, okay, in terms of the eigenvalues, okay, or rather the non-zero eigenvalues, or rather the singular values, in terms of the singular values of this matrix U, okay. I am expressing this image function, okay. What I have done, the diagonal matrix which is composed of the square root of the non-zero eigenvalues, I am pre-multiplying the diagonal matrix by the eigenmatrix composed of the vectors, the eigenmatrix which is composed of psi. Psi means it is nothing but our it is the U transposes eigenvectors, okay, and this is the U transpose U's eigenvectors, okay. So this is pre-multiplied by psi, this is post-multiplied by phi transpose, okay, and we can represent the original matrix U in terms of this particular series. Alright, so this is a very important relation, and since this is being represented in terms of the non-zero eigenvalues or rather the singular values of this matrix U, this transformation is called as the singular value decomposition, or in short form this is written as the SVD. This is called the singular value decomposition. Now just by applying a reverse transformation, okay, we get as follows: capital lambda to the power half, okay, can be obtained as psi transpose U phi, okay. This is obtained as follows. So that means to say that if you are pre-multiplying the image matrix by psi transpose and post-multiplying by phi, okay, then the entire image gets diagonalized. Diagonalized into size, obviously size R by R. The diagonal matrix is of size R by R, and it is very simple to see from here. The image is n by m, okay. Psi transpose is of size R by n, and phi is of size m by R. So what we get totally is a matrix of size R by R, and this happens to be a diagonal matrix. Alright. So again you find over here that this results in a separable transformation, okay. We have a pre-multiplication, we have a post-multiplication component. So this is a separable transformation, and this is called as the singular value decomposition transform. Now there is an important property of the singular value decomposition, and the property is like this, that if I compose an image, okay, UK, okay, as follows. I can compose an entire image if I go from, if I take the summation of square root of lambda m psi m phi m transpose, okay. If I take this, you just remember our earlier relation, if I take the summation from m is equal to 1 to r, I get the entire image, okay. Some error-free composition of image I do, but instead of taking r terms, if I decide to take k terms, some k terms where k is less than or equal to r, okay. If I take only k terms out of this, okay, where k is less than or equal to r, that means to say out of the r eigenvalues, r non-zero eigenvalues, I am taking only k non-zero, the first k non-zero eigenvalues out of it, okay, then the image that I am getting is called as the image u suffix k, because I have retained only the first k eigenvalues, okay. So naturally u is same as uk when k is equal to r, it goes without saying, okay. But when k is less than or equal to r, when k is less than r, then there is going to be some error, and it is seen that the mean square error which I get because of composing the image from only k components instead of r components, okay, the mean square error is the least, okay, when we are applying this singular value decomposition, okay. Let it not confuse you, this result. Again, this gives us an optimal result. So it says that the mean square error, okay, is the least, okay, the mean square error is the least, okay, for this one. But let it not confuse you, because in the case of the KL transformation, what we said was that the average mean square error, the average mean square error was least in the case of the KL transformation, because the average was over an ensemble of images, okay. Whereas for the singular value decomposition, it is a single image that we are taking, okay, and this gives us the least mean square error performance, okay. Now singular value decomposition is, it is used, okay, in the application of image restoration, okay. The singular value decomposition technique is very widely used in image, in the field of image restoration, okay, but not for image coding or image compression, and there is a major reason for this. Firstly, that it is an image dependent transformation, okay, and secondly that there is absolutely no scope for computing the singular value decomposition using a fast algorithm. So you cannot have a fast SVD transformation, and that is why it is not widely used in the case of image coding, or image coding based on transformations, or in image data compression applications it is not used, but it is used in image restorations, okay. So with this we can conclude our discussions on the classical image transformation techniques, alright. And in the next class we will see one application of the image transformation, and that application is related to image coding, okay. So we will see that how one goes about image coding using the transformation techniques which we have discussed so far, and what is the typical compression ratio, data compression ratio that one can get by adopting these many various image compression techniques. Any questions?
So what is the physical interpretation of this SVD equation?
Well, the physical interpretation of the SVD is like this, that we are just composing an image, okay. Earlier in the other transformations we were composing the image as a series summation of several basis images, and all those basis images were pre-computed. Now in the case of the singular value decomposition, okay, the basis image is nothing but the image that is formed out of the eigenvalues, okay, eigenvalues of u transpose and the eigenvalues of u transpose u, assuming the matrix to be of rank R, where R is less than or equal to m, m being the smaller dimension of the image, okay. The matrix which we are, the diagonal matrix which we are forming, okay, out of the eigenvalues, that itself forms the basis image, okay, for the singular value decomposition. Okay. So this is, you can say, the physical significance of the SVD. Any other questions? All right. Thank you.